Hello everyone, welcome to this NPTEL course on Advanced Reinforced Concrete Design. Now we are entering into the week 6. In the previous last week, we discussed about the behavior and design for flexure. So we looked at how to do the moment curvature analysis for RC section, and we also looked at for a singly reinforced section. That means when reinforcements are put only on the tension side, what happens when you start increasing the reinforcement ratio. And finally, also we looked at for a heavily under reinforced section, what is the effect of compressive stress. So then we made some conclusions. So we will continue this discussion and how to do the analysis for RC sections under flexure. In this module, which is 5.3, we are going to talk about what is the effect of axial compression on the flexural behavior, right? So the expected learning outcomes after the student has seen this video, he should be able to derive the moment curvature curves for RC sections under bending, which are also subjected to some level of axial compression. And he should be able to discuss the effect of axial compression on the moment curvature behavior of RC sections. Okay, so we'll see now what is the effect of axial compression. So we know in traditionally in beams, we know that the axial effects are not really considered. The beams are subjected to be axially rigid, and the axial deformations are not really, in strict sense, they are not really considered, or they are assumed to be negligible, right? However, sometimes, depending upon your structural connections, you can have beam elements subjected to some axial compression. If the axial compression level is less than 20% of your concrete compression capacity, then your bending actions or the beam actions will predominate the behavior of the beams. But if your beams are subjected to axial compression, which are higher than 20% of your compression capacity of your section, then your beams will not only be undergoing beam action, there will be a beam column action, because now the compression force also will start to dominate the behavior. Okay, so from your structure analysis, usually if your axial forces are less than 20% of the compression capacity or the compression capacity of concrete section. So for example, here I have taken 20% of F prime C AG. So F prime C is your compressive strength of your concrete, and AG is nothing but your total cross-sectional area of the column. So if I multiply compression capacity multiplied by the area, compression strength multiplied by the area, then I will get what is the concrete capacity of the section in compression. I have not included steel, okay, just for simplicity. If that value is, if the axial load is less than 20% of this F prime C multiplied by AG, then we can say that the axial compression is not really going to dominate the behavior. There will be effect that we are going to study, and we'll see that. So again, what is that we are taking? We are taking a generic, let's say, simply supported beam that is subjected to point load like this, and it is also subjected to some uniformly distributed load. And in addition to that, compared to the previous case, in the previous case, we have taken P here to be 0. But now, this beam is also subjected to some axial compression. Okay, that we have to consider in our analysis. So, anyway, so the bending moment diagrams, there will not be any change because of this axial force for a statically determinate beam like one what we have considered. So you're going to get your bending moment diagram like this. Okay, so there is no issue. Okay, so you get your bending moment diagram from your statics. Then when I'm taking a, let's say, a free body diagram of a particular section, right, on the left side of the beam, now you see here there is going to be a axial compression that is going to act on this section. In addition to that, for resisting this bending moment, now I will have a couple of concrete contributing in compression and steel in tension side contributing to tensile resistance. And then also you'll have shear. So now you're exposing the internal forces because now you made a cut to the section. So you are going to have this kind of a force system that is going to act on this element. Now for a section is also, if you look at it, section is basically a very small part of this beam. So again, there is going to be an axial compression that is acting. And then in addition to that, depending upon the bending moment, you will have a couple of concrete contributing in compression and steel contributing in tension. Now for this, so you can treat the sectional analysis also like a very small version of this. Okay. Now we have taken the free body diagram of a left portion. If I'm taking a small elemental length, then again you will have similar kind of force. You're going to have axial compression, which is going to act towards uh, right, and then you will have compression is going to act towards left, and then tension force which is going to act towards right. So if I write the horizontal force equilibrium for this system for a section, you will find that, so this you can write that as Ts and this you can write that as Cc. That is the convention that we are taking. Okay. So now if I am taking this force system as which is acting towards right as positive, the one that is acting towards left as negative, you will find that Ts is acting towards right, so that would be positive, and then P is acting towards right, that is I'm taking positive, which should be equal to Cc, or in other words, Ts plus P minus Cc should be equal to 0, horizontal force equilibrium, then Cc will go on this side. So if you compare the force equilibrium that we have used for a section without axial compression, now only we said Ts, the tension force from steel should be equal to concrete contribution in compression. So Ts is equal to Cc is what we have considered that as a equilibrium condition. Now there is also an axial compression that is acting in the cross section. So that is going to add on to what is going to be the tension force that is coming from your steel. So the equilibrium equation will be concrete contribution in compression Cc will be equal to Ts plus P. So this is the only change. There is a P that is adding to the tension side. Again, how do you write your tension force? Of course, we have looked at it, right? If I am able to get my strain distribution from the constitutive equation, I should be able to get my stress distribution. Stress multiplied by the area of steel will give me what is the force offered by the steel in tension. Now, P will be given to you from your analysis. Okay. Now, in this case, we are going to see for different values of axial compression, how the moment curvature behavior is going to be there. So P will be given as an input. And then how do you calculate your Cc? You remember, for doing the moment curvature analysis, we assume the top compressive fiber strain, and then we keep incrementing that epsilon C at the top, right? So depending upon what is the value of epsilon C that I'm taking, by integrating the stress, parabolic stress will become difficult for me. So what did we do? We converted that stress block into an equivalent rectangular stress block using Whitney's stress block parameters, which are your alpha and beta. So for a given epsilon C at the top fiber, I will be able to get alpha and beta because these are derived as a function of your epsilon C. Okay. And now this derivation what we have done is valid only for the parabolic stress strain curve model that we have taken. Now if you have to derive alpha and beta for different stress strain curves, for example Thorenfeld stress strain curve that we talked about for high strength concrete, or even for design stress strain curve specified by IS 456, you have to do the integration and find out the expressions for your alpha and beta. Previously, whatever that we derived, it is valid only for the parabolic stress strain curve uh, relationship that we have used. Okay, so once you fix, then you can get your CCS alpha 1 F prime C beta 1 XP. So that is what we have done in your calculation. So this becomes your equilibrium equation. Okay, so this is your horizontal force equilibrium equation. So previously When there was P was equal to 0, it is only Ts is equal to Cc. Now we have an additional component that is coming from axial compression. Now when you look at it, there is a that is getting added. If you look at from your sign conventions of your forces, P is getting added to the tension side. So now let us see what are the implications of that. Okay, again the procedure for your moment curvature analysis is same. We choose top compressive fiber strain in the cross section, right? And then to get my strain distribution, I have to assume a value for x, that is your neutral axis depth. So once I fix my top fiber strain and then the neutral axis depth, then I know plane sections remain plane. So you're going to have a linear strain variations. So you should be able to find out strain at all points along the cross section, right? Once strain distribution is known, I can get the stress distribution from your constitutive equation. Here in this analysis, we are doing parabolic stress strain curve model for concrete. And for steel, what is that we are using? We are using elastic perfectly plastic model for steel. So once the strain values are fixed and the location of your rebar is fixed, then you will be knowing what is the strain in the rebar. Then from your stress strain curve relationship for steel, we should be able to get what is the stress. So once the stresses are found, we can do calculate your CC and we can calculate your T. So in fact, I should say this is T, CC and TS. So because that is in general, I'm talking about compression tension. For concrete in compression, it is CC. For tension contribution for steel in the tension side, we are taking it as TS. So again, we have to satisfy the equilibrium condition. Now, when you have axial compression, what is the equilibrium condition? That's what we saw. Cc should be equal to Ts plus P. So the P is adding it to the tension contribution of the steel. So if this condition is satisfied, then whatever the assumed neutral axis depth is correct for us. If it is not satisfying, for example, let's say if your Ts plus P is coming to be higher than your Cc, right? Then what is that we need to do? We need to increase the value of Cc. So how do we increase the value of Cc? We have to increase the neutral axis depth x, okay? Or if your Ts plus P coming to be, sorry, in this case, your C is, okay, this is correct, Cc is less. If Ts plus P is less than Cc, then you have a higher value of Cc. In this case, you have to decrease neutral axis depth. So we have seen that in your pure flexural analysis, right? So now, if you have to see for compared to a single reinforced section without P, now we have an additional component P. So what will happen for the same section with same strength of the concrete that what we are considering? So what will happen? You are going to have a more value on the tension side, right? So because there is P value that is getting algebraically added. Okay. So what will happen? So to satisfy, so when you have axial compression, we will find that the neutral axis depth required, right, has to be, this is going to be higher. So this has to be increased. So the X value will go up. Okay. So that we will see. So once the equilibrium condition is satisfied, then we know all the internal forces. Then you can take moment about any point along the cross section to get your moment resistance, right? And then we know curvature. How do you calculate your curvature? Curvature is a rotation of a section. So curvature is nothing but phi, which is written as epsilon c divided by x. Okay, so we have seen this. Okay, this is your rotation of your section. Okay, so this is your curvature. So now for one assumed value of epsilon c, I get my moment resistance and I get my curvature as well, right? So let us see one example problem how this procedure is done. So in this case again, I am taking the same cross section, okay, that what we have done in the last part of the module, right? So 600 mm by 400 mm cross section I am taking, and it is having an effective cover of 550 millimeter with the area of steel of equal to 1200 millimeters square. Now again, what is the percentage of steel that we have put? How did we calculate? We calculate that as rho, which is nothing but AST divided by P into H multiplied by 100. Okay. So for this value, if you remember, 1200 divided by 400 multiplied by 600 multiplied by 100. If you look at it, it is going to be half a percentage, 0.5 percentage. It's a very, very small amount of reinforcement. And we have seen that this section is an under reinforced section. So before concrete was reaching a fiber strain of 0.0035, the steel yielded quite a bit, right? So it's a heavily under reinforced section. For this section, let us see if I am taking an axial compression of P is equal to 0.1 F prime CAG. Now, if you go back, what is the F prime C that we have taken? 40 megapascal and the yield strength of 500 megapascal. So, 0.1 F prime CAG works out to be how much? So, P will be equal to 0.1 multiplied by 40 multiplied by AG is nothing but 400 multiplied by 600. Then when I divide by 1000, I get it in kilonewton. So if you do the numbers, you will get 0.1 multiplied by 40 times 400 times 600 divided by 1000 works out to be. So if I'm taking 40 percentage for the entire area, it works out to be 960 kilonewton. So you can check the values. Okay, it is working out to be 960 kilonewton. Okay, that is the level of axial compression that I have considered. You see here, this is only 10% of compression capacity of concrete only. Here I am not even including steel. So you see that very low levels of axial compression this particular section is subjected to. Now we will do the moment curvature analysis and then see what is the effect of this, right? Okay. So again, so how do we do the moment curvature analysis? We have seen we select this strains of different values, okay, at the top fiber of concrete in compression. So these are all epsilon C values at the top fiber, which is in compression, right? So I'm slowly incrementing it. So I take first a small value of 0.0009 and then I subsequently keep incrementing it. So now we have done this calculation. P worked out to be 960 kilonewton, which is about 10% of your concrete capacity of section in compression. Now what I am doing is I am fixing this epsilon C. So this is epsilon C for the first value, because what we do is we keep incrementing your epsilon C at the top fiber and then we do the analysis, right? So now when I'm putting epsilon C 0.0009, now you can ask me how did I come up with x is equal to 275 millimeter. I am assuming this, okay? Now for this 275, once epsilon C is fixed and x is equal to 275 is assumed, then you can find out all the strain, because from your similar triangle principles, it's very simple, right? So we can find out. So from the strain distribution, now I should be able to get what is the strain on the tension steel, which I'm denoting here as epsilon T. So from similar triangle, we know that this distance is 0.0009 by 275 should be equal to, and what is this distance? We know that it is equal to D minus X. So that is what I have written here. So epsilon T by D minus X should be equal to 0.0009 divided by 275. From this, I can find out epsilon T, which is 0.0009, because my neutral axis depth I have taken as half of D. So epsilon T is also, I'm getting same value as your epsilon C. Now, what are the implications? If you go back to your stress strain curve for steel, what is that we have? Fs, epsilon s, what kind of relationship that we were using? So we have chosen straight like this, okay? And this value was your Fy, which is equal to 500 megapascal, right? Now, what is your yield strain that we have taken? Taken to be 0.0025. Now, where are we in the stress strain curve? It's a very small strain. So, what is the let's see. So we are somewhere here. It's a very small strain. So still the steel has not yielded. So I can get my stress as epsilon T multiplied by elastic modulus, because it's still linear in the linear elastic regime. right? So you get a very small stress, and area of steel is given as 1200. Then when you divide that, you get a tension force from steel of 216 kilonewton. Now, the thing is, again, what kind of strain distribution that you will have for concrete? Again, if you see concrete, where already we have drawn here. Okay. So where are we? We are in this regime. Okay. So we are in this regime. So here also the stress, because the strain is very small, pretty much we can assume the stress strain relationship of concrete also in compression, because the top fiber strain what we have considered is so small, the stress strain relationship can be assumed to be linear. However, when the stress levels or when the strain levels becomes higher, then you know that this linear elastic assumption for concrete in compression is not valid. It is going to become parabolic as per your Hognestad stress strain curve model. Now let us see. So what is P? So now see what is the force equilibrium. Again, force equilibrium is P plus Ts should be equal to Cc. Okay, P is now adding on to this. Now there is a P that is acting 960, and I got 216 of tension value. So this is a total force that is acting towards right. Now that has to be balanced by Cc, that is going to act towards left. We have seen it in your force equilibrium. Right, now let us see what is Cc. Right, so we got this value. Okay, 1176. Now again we are going to use rectangular stress block parameters, but integration will become difficult. So that is the advantage of any stress block, triangular or a parabola up to peak, or a descending parabola. I can convert them into an equivalent rectangular stress block with alpha beta parameters. That is a big advantage with this. So let's say for the assumed epsilon c of 0.0009, once epsilon c is fixed, I should be able to calculate alpha and beta. Now let's see what is beta. Beta we have derived that. It is 4 minus epsilon c by epsilon prime c divided by 6 minus 2 into epsilon c by epsilon prime c. Now what is epsilon prime c? It is a strain at which the concrete is going to reach peak stress of 40 megapascal in compression. That for a normal strength concrete up to 40 megapascal, epsilon prime c is considered to be constant value of 0.002. Okay. So of course this epsilon prime c is going to increase if I am going for a high strength concrete, which we are not worried about right now. We are looking at a 40 megapascal concrete. So once you fix your value, beta 1 works out to be 0.70. Now what is alpha 1? Alpha 1 is 1 by beta 1 times epsilon c by epsilon prime c minus 1/3 of epsilon c by epsilon prime c. So once you plug in your number, you get an alpha of 0.55. So once alpha beta is known, what is Cc? We know that equation Cc is alpha 1 f prime c beta 1 times xu. Now we are dealing with a rectangular section which is having a constant width. So you see, so this is your B. So alpha 1 is known, right? F prime C is known, beta 1 is known, xu is assumed to be 275, P is known. So let's see now what are the force that we're getting. So you see here I'm getting a force of 1694 kilonewton. Now what is the total addition? Is the equilibrium condition satisfied? What is the equilibrium condition that we said? P plus Ts should be equal to Cc. Now what is Cc? 1964, which is higher than P plus Ts of 1176. So what is it? Now Cc, you have a much higher value. I have to reduce the value of Cc. Now for a particular strain of 0.0009, how can I? Alpha is fixed, F prime C is fixed, beta 1 is fixed, B is fixed. The only way I can reduce Cc is by reducing the value of neutral axis depth. So whatever that we have assumed to 275 mm is too high. Okay, so I have to use a lower value of your neutral axis depth. So that is what we have to do. So we have seen that. So so in fact this should be Ts plus P. Okay, so we have to decrease the value of your x. So now let's say I'm taking x is equal to 212 millimeter. Let's repeat the calculation from strain distribution. Now you got a strain of about 0.0011, because neutral axis depth is going up means for a particular top fiber strain, if I'm reducing neutral axis, strain in the steel on the tension side is going to increase. So that is why it has increased. So my tension force is also going to increase. So again, when you add P plus TS, it is 1306 kilonewton. And now again, alpha, beta, everything is fixed. Only thing is I have reduced X, which if I change it, then it works out to be nearly 1305. So now you see that P plus Ts is equal to approximately Cc, nearly same. So that means we have achieved our horizontal force equilibrium. Now for this assumed strain condition of top fiber compressive strain of 0.0009, neutral axis depth of 212 millimeter gives me horizontal force equilibrium. So this is the correct strain distribution. Okay. Now that we have got that and we have also got the forces, now we can draw the forces. Okay. So now you see here compression forces acting towards left. So which is this, and then P, this is your P and this is your TS. Now all these locations also we know. Where is P is going to act? P is going to act at the centroid of the cross section, right? So, which is nearly same. So now how do I get my moment resistance? I can take moment resistance about any point, but it is easy if you do it at CG of the cross sections. When you take CG, the P will not come into the picture. So you just to deal with CC and your tension force. So if I for this section moment resistance, if I have to take, what would be the moment resistance? 1306, which is a CC that is acting towards left. So if I take moment about the CG of the section, it is going to create a anti-clockwise moment. So that I can write that as anti-clockwise moment. Okay. If I'm taking it about the CG of the cross section. So what would be the distance at which it is going to act? So we have seen that this distance is beta XU by 2. Now what we are looking at it is, we are looking at distance of this distance is what my lever arm is. Okay, so this lever arm is how much? Is going to be h by 2, which is your depth of your section, divided by 2 minus beta xu by 2. So it is going to create. Okay, now if I take this again, let's say anti-clockwise moment is taken as negative or positive. Let's say it is a positive because moment anyway will add up to be positive. So again, 346 your tension force. That is also, if I take moment about the CG, it is going to be acting in the counterclockwise direction. So both are same sign. So it will add up. So TS. Now what would be this lever arm when I take moment about CG? This is going to be, what would be this distance? This distance is going to be, right. So what is this distance? It is going to be D minus H by 2. So it is D is your effective depth minus H by 2. Okay. So this will be your moment resistance. Now why P is not coming into picture? Because I'm taking moment at the CG where the P is passing through. So it is not having any lever arm to create moment resistance, right? So this is the way we do it. So we get this. Okay. Here anyway I've taken D as H. D is equal to H. Okay. Overall depth and H are written same. So effective depth is 550. So if you do the numbers, both of them will add up and you get a moment resistance of 381.3 kilonewton meter. Now if you go back, when your P was 0, when P was 0, when P is equal to 0, same section, when we analyzed, you get a moment resistance of some value. That is going to be slightly lesser than what we are getting here. Okay, now let's do the analysis for this. So now what is the curvature? Curvature is again epsilon c by x. So you get 4.25 into 10 to the power of minus 6 per millimeter. Now we can keep continuing doing the analysis. P remains same. So for a particular section, for a beam, axial compression is given. It's going to be constant. It's not going to change. Now what I'm doing is I'm keep uh, increasing my epsilon c. So if you go back to your stress strain curve model again, now where is the epsilon c? So this is the model that we have considered, right? I have c, epsilon c. Now where is the So take the red color. So previously we considered this value, which is 0.0009. Now I am considering this value. What is this value that we have taken? Epsilon c equal to 0.0015. Now this value, you know, it is equal to epsilon c equal to 0.002, which is your peak strength. So slightly lower value that we are taking. Okay. So this is the value that we are doing the analysis. Okay. The corresponding to this. So now previously I have got my epsilon c. Now when epsilon c is increasing, of course, more stress is going to come. So I'm going to take a slightly lesser value of x. So again, you have to do it through iterative process. So by looking at the numbers. So again, from similar triangle, once x is fixed and top fiber strain is fixed, then I will be able to get all the strains at this location. Now I'm calculating epsilon t from a similar triangle. Again, we know that this distance is nothing but your d minus x. Okay, so once x is fixed, then you can use your similar triangle and you get a strain of 0.0033. Now for this, you can see that now it has gone beyond your yield strain. So yield strain was 0.0025. So this is higher than yield stress. So stress offered by the steel is going to be remaining constant at a value of 500 megapascal from your sustained curve, right? So tension force is going to be 5. That's why I'm taking stress is going to be 500 multiplied by 1200. When I divide by 1000, I get it in kilonewton. And forces generally we deal in kilonewton. Moment we deal it in kilonewton meter. And curvature is a small value, so we deal it in 1 by millimeter. So if you look at your axial compression or the force that is acting towards I would say right. So it's going to get 1560 kilonewton. Then now see alpha and beta corresponding to the previous value is applicable only when epsilon c is 0.0009. Now epsilon c has increased to 0.0015. So again I have to recalculate my alpha 1 and beta 1. Okay, so that works out to be 0.72 and 0.78. And now once alpha 1 beta 1 is found out, I can calculate my compression forces 1557.2 kilometer. So you can see that nearly 1560. Probably if I have to slightly increase the x value of instead of 173.3, maybe I should take 173.32 like that, 32. So it's not going to make a big difference. So we'll find that the equilibrium condition is satisfied. So once equilibrium condition is satisfied, so assume the strain distribution is correct. So we can go ahead and calculate now moment resistance. Same, exactly same process. Now, if you see moment about the mid depth when you take again, so this is going to act like this in counterclockwise. Again, this is going to act like this, okay, because I'm taking moment about this point, okay. So both of them are counterclockwise, it is going to add. So now what is it? Ts multiplied by d minus d by 2 is your lever arm, and cc, and this is your lever arm. So this lever arm is how much? Again, we have talked about. It is going to be d by 2 minus beta 1 xu by 2. So that is this distance. So that is your lever arm here, okay. So 1 is 2, both of them are counterclockwise, so we are adding it up, so that is going to be moment resistance. Then you see that you get a value of 520.7 kilonewton. Now curvature is going to be epsilon c by x, then you get 8.65 into 10 to the power of minus 6 per millimeter. So again, curvature, what is section? It is a sectional rotation. You are dividing a strain value by neutral axis depth. So it is going to have a unit of 1 by millimeter. So we should have it. It is a sectional rotation. Okay. Now again we can do the calculations for a failure strain. So usually we take a failure strain when concrete at the top reaches a compressive fiber strain of 0.0035. Okay. So for this top fiber of 0.0035, now again I have to reiterate and find x. Now in this case I have already done it, and I know at x is equal to 133.7 it is going to satisfy the force equilibrium. So that is why I'm showing only for this calculations. Now you can, if you program it in an Excel or a MATLAB, quickly you should be able to, for all the points, we should be able to get your moment and curvatures. Okay, so again from similar triangle, epsilon t works out to be 0.0109 because previous iteration itself the steel has yielded. Now when you are subjecting it to more rotation, more strain at the top fiber, which is going to lead more strain on the tension side as well. Obviously, the strain in the steel is going to increase. So that's what we are seeing. So now the TS again, this value is higher than 0.W, so Fs is going to be 500. Okay, 500 megapascal. Okay, which is reaches yield. Okay, so that's why we are taking 500 multiplied by area. That is going to give me tension force of 600 kN. Now again, when you add them up, 1560. Because now that steel has yielded, the previous iteration also we got 1560. Here also we are getting 1560. Why? T remains constant. TS also is not going to increase because already it has yielded. So you get P plus TS, or in other words, the force that is acting towards uh, from, let's say, from left to right, you are going to have 1560 only. So equivalent concrete force that is going to act from right to left. Okay, so that CC is basically compression force. It works out to be nearly same. Now why CC? Again, beta 1 and alpha 1 you have to recalculate because it is function of what is epsilon C at the top fiber, right? So you see here the equilibrium condition now is satisfied. So what is the equilibrium condition? Again, Cc should be equal to P plus Ts. That is your equilibrium condition. Nearly it is same. So you have found it. So now if you want to slightly get it even closer, 133.7 will become 133.71 or so. So, but I think we are all structural engineers. So this is good enough, right? So this is equilibrium condition is satisfied. So again, we calculate the moment resistance. So when you do that, again we do this when I take moment about this point, there is no contribution. So this is going to act like this, and this is going to go act like this. Both of them are counterclockwise, and we have already talked about your lever arm. Okay, Z1. Let's say this. Okay, call it as Z2. So this is your Z2, and this is your is at 1. So we know how to calculate that. So if you do that, again your moment resistance now as so 524.1. So the moment again the steel starts yielding, there is not going to be a big change in your moment resistance, but the curvature will increase. So the curvature now has increased to 26.18. Again, how do you calculate curvature? Top fiber strength. So curvature is nothing but this rotation. Okay, this rotation we know how to calculate, which is epsilon c divided by your x. Okay, so that is why curvature we always calculate it epsilon c divided by x. Okay, so which is 0.0035 by x in this case is 133.7 millimeters. So that works out to be 26.18 times 10 to the power of minus 6 1 by millimeters. So this is what we got, right? So now for a particular section that what we have taken, we keep incremented your top compressive fiber strain, and then you are able to get moment and curvature values. So now if you plot this, so this is the curves that we have done the calculation. Okay. So this red color one. Okay. So this red color is one. Now what is this black color? Black color is the same section 400 by 600, but an AST was 1200 mm². Now in this case, P was equal to 0. Now you see here, the moment P we have put 0.1 F prime CAG, which is 980 kilonewton. You see here what has happened to the moment curvature behavior. My ultimate moment resistance, this is about 310, right? And here in this case, we got about 532. So 310 has become 532. Now, what is the curvature at failure? We got a value of about 70 or so. Okay. Now, what is the curvature at failure here? This curvature at failure is, let's say, this is the value that 26 point. So 26. So what can we infer? A small amount of axial compression, which is 10% of your concrete capacity in compression when I put it in the beam. Now what has happened? The moment resistance, the peak moment resistance has increased from 310 kilonewton meter for the section that what we have considered to 532. So putting small amounts of axial compression helps in increasing the moment capacity. Now we can also see the stiffness. Now what is stiffness? In flexural stiffness, moment divided by curvature is nothing but your flexural rigidity, EI. Okay. Now this EI is not going to remain constant because we are doing a nonlinear analysis. It's going to keep reducing. Initially, E will be high value, I will be high value. As more cracks are forming, E will start slightly reducing, I will also reduce significantly. So your stiffness will. But if you compare the section without axial compression, the presence of axial compression has increased the flexural rigidity. Or in other words, the slope of this moment curvature behavior is basically your flexural rigidity. So we can say presence of axial compression at a lower levels or small levels up to 30% of concrete capacity usually helps in increase in your moment resistance. However, what is that we are doing? The curvature at failure now has reduced from 70 to 26 or so. So there is an increase in moment capacity, but there is a decrease in your curvature at failures. Or in other words, the sectional rotation capacity has reduced because of presence of axial compression. So like this, you can plot for different values of epsilon c, what are the different moment and different curvature. So when you plot it, you get this kind of a red color curve. So presence of axial compression increases moment capacity and decreases the curvature at failure. It is also going to help in increasing the stiffness of the cross section in flexion.